Yeah, so we've been looking at the test on one mean. In our previous class, we looked at a confidence interval on one sample mean, and we quickly did some revision and tackled an example on regression before. Okay, we ended the class. Today, we want to continue with the test on two means. Okay, and for the differences of two means, when we talk about two means, then we are talking about two population what means. Okay, so we have information from two different results. So, for example, there is an existing way of planting some breed of crops, okay, or corn. Let me just take corn for an example. And then you want to test the effectiveness of a new fertilizer brand. So it's going to be the crops planted using the normal procedure as against crops planted using what fertilizer. Okay, that is where we have the difference in the two populations. Okay, so crops, okay, with normal technique, and then crops with what with fertilizer. Good. So we have population, and at the end of the day, we are going to test the yield of the number of crops here. Okay, so we'll have the average yield. Let's say y1 here. Okay, and then we also have the average yield from uh, farm 2 with fertilizers, which will be what y2. And we want to compare. The objective here is to compare whether there is a significant difference. Okay, when I say difference, I mean whether y2 minus y1, okay, will be greater than y1 bar will be greater than what? Zero. Okay, or better still, let me put it this way, will be first of all equal to what? Will be equal to zero. If they are equal to zero, then what it also means is y2, the average of population 2, is equal to what? The average of what? Population 1. So in other words, there is no difference between applying fertilizer and what? The normal technique. Okay, that is what this test brings on board. Now there are two main types of differences we'll be looking at. We have situations where the populations are independent. Independent means the crops which were planted using the normal techniques are different, okay, are different from the crops which were treated with what? Fertilizer, okay. So the yield y2, okay, has nothing to do with what? Normal technique. They were not influenced by the normal technique, neither was the yield in the normal technique influenced by those in the fertilizer. We say that we have two independent what? Population what? Means. Okay. And like I said, the objective is to test if there are differences in the population means, okay, or whether the difference are what? Significant. Now, with regards to the sampling distribution of two population means, which are approximately normal with known variances. Okay, we write that the difference, okay, of y1, that's the two population, is also normally distributed. mm, uh, with a mean of mu1 minus mu2, okay, from the population. Mu1 population mean 1 minus population mean 2. Okay, and then what? The variance, this time we have the standard deviation, which is what? Sigma 1 squared over n1 plus sigma 2 squared over what? N2. Okay, good. And since usually since you see, if it had been in the case of the corn, okay, we have normal and then we have fertilizer. uh, because we are still dealing with corn breeds, and we know that the population average for a corn breed is always going to be the same. Okay, it's always going to, the population for the corn It's always going to be the same. We don't expect much of a difference here. So this difference, okay, which usually we refer to as the difference. Some use d, some use the delta, okay, which is what mu mu1 minus mu2, okay, is usually equal to what is equal to 0 unless clearly specified in the example, okay, that there is some difference which you have to test for, okay. So in the test statistic, we'll always be left with what the observed difference, which is y1 minus y2, okay, minus, it should have been minus the what, the mean of the sampling distribution, okay, but we know that this, okay, approximate 0 because the difference is usually 0, so that term will not come. Good. Over the standard deviation, which is what the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, okay, where sigma 1 squared is the variance, the variance, sigma 1 squared and sigma 2 squared are the variances for the two populations respectively, okay. And in the case where we do not know them, okay, we will use what the sample standard deviation or the sample variances for the two populations, okay, in estimating the unknown population variance, okay, but we'll come to that later. Okay, so in very basic terms, what we are saying is to, okay, test for the hypothesis tests, to conduct a hypothesis testing on the difference of two means, okay, your null hypothesis is always, the key objective is always what, that mu1 is equal, mu1 minus mu2 is equal to what, a certain difference, or usually the difference is 0, okay, or we can be testing whether mu1 is greater. We can also have whether mu1, okay, mu1 minus mu2 is greater than the difference, or mu1 minus mu2 is less than a certain difference, or mu1 minus mu2 is not equal to what, a difference, okay, which will also lead us to the corresponding rejections. If it is less than the difference, then we are talking about a one tail left hand test where the rejection is on the left hand. And then if we are talking about greater than, then we are talking about a right tail test, okay, where the rejection is on the right hand. And if we are talking about not equal to, then we are talking about two tail tests, okay, where the rejection is on both sides. So you're going to read set alpha on 2, like we said in the previous class. And the test statistic, like you've already seen, there's a general form, but usually this will be given as what, 0, okay, because usually the samples come from the same what underlying population. Okay, let's go on to the next point. So we have an example here. Let me clear the screen first. So we have an example. It says a newly manufactured drug A is said to decrease the mean weight of obese individuals more than the normal procedure, okay. Two different groups of obese individuals were administered these two drugs, with the first group receiving what, the normal procedure or the placebo. So that is group 1. And then those with drug A, which is group 2, also receive group the drug A. Group 2 received drug A and observed for a week. The experimental results are shown. So this group 1 is for the placebo, that's the normal, okay, procedure. Normal procedure is group 1, okay, that's group 1. And then those on drug A are in group 2, okay. And the objective here was what? To check, you see, it says drug A is said to decrease, okay, to decrease the mean weight, to decrease the mean weight. So it means that at the end of the day, we expect that the weight of the individuals in drag A will be less than the weights in drag A, okay, should be far less than what? The weight in what? The normal procedure, okay? This is the expectation that the average weight in drag A should be less than the average weight in the normal procedure. That is if indeed drag A reduces the mean weight better than the normal procedure. If that is so, then it means that one of our hypothesis is going to be, let's move on. Yeah. Okay. So if that is so, then we are saying that mu2, right? Mu2 is for drag A. So mu2, the average for drag A, okay, should be less than, we were saying less than what? Less than the average for what? Drag A, okay? Which also means that we can rewrite this hypothesis as what? Mu2, okay, minus mu1, okay, should be what? Should be less than what? Should be less than the difference, okay? And the opposite statement for this statement will be what? Mu2, okay, minus mu1 should be what? Greater than or equal to the difference. Okay, good. And then since this has the equal to, this should be the null hypothesis. This will be the null hypothesis. Okay, that's H naught. And then this will be the alternate hypothesis. So let's write it properly over here. So this will be, okay, but because this time we have mu1 coming first, this will rather be less than or equal to, and then when it comes to mu1 minus this, the objective is for this to be greater than that, okay? Good. Or we can still rewrite what we had initially here, which is going to be what? H naught, okay? H naught is what? Mu2, okay, mu2 minus what? Mu1, okay, which is what? Greater than or equal to what? The difference. And then your H1 here, okay, will be mu2 minus mu1 is what? Is less than D, okay? It's nothing difficult, okay? If we are writing it in this form, it's the same as this. It's just like multiplying through by a negative sign, a negative one. Once a negative one runs through, this will be positive, this will be negative, and the sign will change to less than. It's the same thing. Okay. Then the next thing is to write your level of significance, okay, which will be alpha is what? 0. What? 0.05. Okay. And your test statistic, like you know, is stated here, okay? But as I told you earlier, this is going to be 0. And then we've been giving y1. We're also giving y2, okay? And then we're giving the variance of the population to be 4.8 respectively, and the sample size to be what? 35 and 36, okay? So do the calculation for me. Find 63 minus 2 over 53.8 over the denominator. Calculate it for me. Let me have the answer. Okay, so Steven says he has 8.249. Thank you. Okay, then the next step, Prince, did you get the same answer? Okay. So the next step is to read your critical what value, okay? And in so doing, like we already aware, uh, once the sign on your alternate hypothesis is what? Yes, before we read a critical value, there is something you need to know, okay? If we expressed your hypothesis in this form, okay, you see, we've expressed it as what? Population 1 minus population 2, okay? So when we came here, we came to subtract y2 from what? Y1. Take note of that. Mm? So the group that comes first in your hypothesis, if we're going with this hypothesis, then this becomes what? The term here, y1 minus what? Y2. But if we have mu2 minus mu1, then you should rather have what? Y2 bar, okay, minus what? Y1 what? Bar. And then this should be sigma 2 squared plus what? Over n2 plus sigma 1 squared over n2. Anyway, addition is commutative, so that doesn't matter. But the numerator, it will matter a lot, okay? Because y1 minus y2 will not be the same as y2 minus y1. Okay, so we have 8.249, okay? And again, our test, we said we are dealing with this hypothesis here. Let me clear this side first. Yeah, so we are dealing with the hypothesis of this being greater than that, okay? So, which means we are dealing with a right tail test, a right tail test with the rejection to the right hand. And our alpha, okay, will be the full 0.05. Okay, so it means you are reading Z alpha from the table. So read Z alpha from your table for me. You find 0.05. Okay, we know how to do it, right? Either if you're reading from the right hand table, then you subtract from 1, and then you read 0.95, okay, and then find the set the critical value, which gives us that probability value. Good. So 0.025, okay, we know is 1.96. Okay, we know that from previous examples. So this is it. So the Z value here will be 1.96. Okay. So let's go back to the previous screen. So which means that our rejection region here is what? 1.96, 1.96, okay, which is the critical value, okay. And then, like we said, all you need to do now is to compare your Z calculated value with the graph, and then we'll realize that the center is 0. So we'll realize that our calculated value, okay, the calculated Z-score value is on the extreme right of your critical value, which means it lies in the rejection region. Okay, so once this lies in the rejection region, we have evidence, okay, to reject the null claim. This is the null claim. We have evidence to reject this null claim, okay. And once we've rejected the null claim, what we are saying is, indeed, mu1 minus mu2 is greater than what? Is greater than a certain d, but in this case, our d is what? Is 0, okay. So there is a significant difference between what the mean produced by the normal procedure, this for the normal and then these are those on drag what 8. Okay, so the difference between those in the normal technique and those in drag A was very huge. It was very significant at a 5% what alpha value. That is what we are saying from this example. Any questions? Any questions?
No, sir.
Okay. So I'm going to touch on two other aspects. The class is going to be quite brief, considering the fact that you are still writing exams. There is another example here. Okay, still on this same uh, uh, topic. He says product developer is interested in reducing the drying time of a primer paint. Two formulations of paint are tested. Formulation 1 is the standard chemistry, and Formula 2 has a new drying agent that should reduce the drying time. From experience, it is known that the standard deviation of drying time is 8 minutes. Okay, so the standard deviation of the population in this case is what is known. Then, and this inherent variability should be what unaffected by addition of the new ingredients. 10 specimens were painted with Formula 1 and another 10 specimens painted with Formula 2. The 20 specimens are painted in random order. The two sample average are what? One, that's for population 1 is what? 121, and for 2 is 112. What conclusions can the product developer draw about the effectiveness of the new ingredient? Okay, yeah, so here we are, the main focus here is we are testing if what Formula 2, the new drying agent, okay, reduces the drying time better. Okay, so reducing means you shorten the number of minutes in drying, in the paint drying. So in our hypothesis here, our focus is what? That the mean okay, drying time for Formula 1 minus the mean drying time for Formula 2, okay, will surely be greater than what? 0, because we expect this one to be less, far less. The average will be far less than that in the first technique. And then the alternates, the contrary statement will be mu2, okay, is less than or equal to what? 0. And of course, we know that this will be the null hypothesis because it has the equal to, and then this should be what? Our alternate hypothesis, that's HA, because it is directional. Okay, good. Then the next step is to state your alpha level. Third step is, we know that the population is normal with sigma population variance known. So we use the set test statistic, okay, which we've already seen. And then all you need to do is to use your, take note once again, because we are using mu1 minus mu2 is greater than 0. You bring x1 minus what? X2, okay? But if you change it, then it's going to be what? S2 minus what? X1, okay? Take note of that. We have to check if the difference between the two is what? Exceeds 0. Yeah, so once you test for your statistic, the next thing is to what? To test your critical value, okay? And then once again, we are dealing with what? A right tail test, okay? Which will still be 1.96, okay? And then checking for this value, which will be on the right of 1.96. So we have evidence to reject the null claim. So we're going to reject the null claim here, okay? Which simply means that mu1, the difference between the first formula and the second formula is significant, okay? It's greater than what? Than 0, okay? Which means that there is a big amount of difference between the first formula and the second formula. And indeed, the second formula is effective at what? Reducing the drying time of the paint. Okay, now let's move on to the next condition. In the case where your variance is unknown, population variance is unknown, or even the sample standard deviation is not provided, uh, there are two cases. The first case is where we assume, even though we don't know the population, we assume that the two populations are coming from the same what? The two samples are coming from the same population, okay? Uh-huh. With equal variances, even though they are not known, okay? Now, again, if our sample size in this case is small, if the sample sizes are small, then you have to make use of what? The student t distribution. Like in the case of the test of small means, of one means, okay? We said that if the population is normal and variance is not, use the set. If the population is the variance is not known, then there are two cases. The first case is when n is greater than or equal to or 25, okay? If it is, then by CLT, we can use the set distribution and then use the sample standard deviation to approximate what? The population standard deviation, okay? And then when the sample size is less than 25, we use the t distribution. So it's the same case here. So in this case, when the variance is known, we use sets. If the variance is unknown, like in the first case, okay, you ask yourself, is the sample size large? So is N1 greater than or equal to 25 and N2 also greater than or equal to 25? If it is so, then you still use the set and then approximate with what? The sample standard deviation. But if not, what do you do? Okay, now you make use of the t distribution as you can see here, okay, and the distribution, I think we are familiar with this. That will be x1 minus x2 minus, okay, mu1 minus mu2, okay. But because we are saying that the populations are are, are the same, the sigmas or the population of the two the two sample, okay, is the same, then essentially their population mean is also likely to be what the same, which means that the difference will also go toward zero. Good. However, the little difference here is, which we have to take note of, is that in the t distribution we are going to compute for what we call as the pooled, okay, the pooled variance, the pooled variance. So we have the pooled estimator, which is a weighted variance. So you calculate for SP. SP is given as a square root. SP, that is SP squared, is N1 minus what? The sample size for population 1 minus 1 times what? The standard deviation for the population 1 squared, or the variance for population 1, plus the sample size for population 2 minus 1 times the variance for population 2 over n plus n1 plus n2 minus 2, which is also the degrees of freedom, which is the degrees of freedom when reading the t distribution. Okay, so this is the only new thing here. We are going to calculate for our, okay, pooled standard deviation here. Okay, and then once you finish, you find the square root, okay, to give you your SP. Don't forget, you find the square root to give you your SP. Okay, so let's see an example on that. Good. This further notes on the same thing. Okay, so like we said, our null hypothesis will still be the same because we are testing on the difference of mean, and then our test statistic will also be the same. The only difference is what? Calculation of your pooled what? Standard deviation. Okay, and then the decision is also going to be the same. But here you take note, we are going to, the degrees of freedom is going to be what? N1 plus N2 minus 2. Okay, that is what we have to take note of. But you take into consideration the sign on the alternate hypothesis to determine whether it's a left hand, right hand, or two-tail test. Okay, then we go on to the example. So we are saying that two catalysts are being analyzed to determine how they affect the mean yield of a chemical process. Specifically, catalyst 1 is currently in use. So that is the placebo, the normal procedure. But catalyst 2 is acceptable. Okay. Since catalyst 2 is cheaper, it should be adopted, providing it does not change the process yield. A test is run in a pilot plant and results in the data are shown in this table. Okay, is there any difference between the mean yield? Okay, use alpha equals 0.05 and assume equal variances. Okay, and like you can see, the source is from the reference text, which is Montgomery. Apply probability and statistics for engineers. Okay, so we have the data. Okay, the mean yield for 8 observations. Okay, 8 observations for catalyst 1 and for catalyst 2. So the first thing that you do is to find the sample what mean for catalyst 1, and then the sample standard deviation for catalyst 2, then same for catalyst 2, okay, and the standard deviation for catalyst 2. But we have to take note of the fact that in this case, this is not known, okay, sigma squared is unknown, okay, we do not know it, it was not given. That is why we are estimating the sample standard what deviation, okay. But we are assuming that since we are coming from the same what population, then the population variances should be what equal. Okay, now let's go to the tests. Okay, so in the test procedure, like we said earlier, okay, is still going to be, let me create a page for that. Okay. Yeah. So we know the sample size is 8. N is 8 for each population. So N1 is 8. N2 is also what? N2 is also what? 8. Okay. And then we do not know sigma square. So it means we are falling on the t-test statistic. But the objective here, let's go back to our question and then check our objective. Our objective is to check. It says it's acceptable. So we want to test run and determine, is there any difference between the mean yield? Yeah, because now here we are talking about costs. Catalyst 2 is far cheaper than catalyst 1. So we want to check whether catalyst 2 is, equivalent or is close to the impact of catalyst 1. If it is, then it means we can follow catalyst 2 at a cheaper cost. So that is our objective, which means that our hypothesis is going to be what? We are looking at mu1, okay, minus mu2. We are testing if mu1 minus mu2 is going to be equal to what? 0. Okay, and then alternatively, this will be mu1 minus mu2 is not equal to what? Is not equal to 0. So that's for step 1. Then in step 2, we have our alpha level, okay, which is what? 0.05. In step 3, okay, we know from these conditions that sigma squared is unknown and the sample size is less than what? Is less than 50. Okay, that's the summation of the two is less than 50. So we are saying less than 50 instead. Less than 50. Okay. So we fall on the student t distribution, which is what? Which is we have x1 x1 bar minus what? X2 bar, okay, over our s put, okay, s put, okay, square root of what? 1 over n1, okay, plus what? 1 over what? n2, okay, good. And we're giving the mean. Let's go and write that and then come back. So we are giving x1. Let's write that in the corner. So x1 bar is giving us what? 92.255. Then s1, okay, is giving us what? 2.339. Okay, whereas your x2 bar is 92 point what? 92.733. And then the s2 is 2.98. Okay, so let's go back to our page. Okay, so we're first going to calculate, we have to calculate s put, and s put we know that is a weighted, so n minus 1 times what? S1 squared, okay, plus what? N2 minus 1 times S2 squared over N1 plus N2 over what? Over 2. So let's go back and do the calculation. You have to help me with the final estimation. So SP will be what? SP will be just a minute, please. So SP will be, I'm sure you are doing the calculation by now. So we know it's N1. N1 is what? 8 minus 1, okay, which is 7 times S1 square, which will be 2.39, okay, 2.39 squared, okay, plus 8 minus 1, 8 minus 1, so 8 minus 1 times what? Your S2 is 2.98 squared. Please do the calculation for the numerator so that we don't waste time. Over 8 plus 8, which will be 16, minus 2, which is 14. Okay, so calculate it for me. 7 times 2.39 squared minus plus 7 times 2.98 squared over 14. Okay, so we'll go by Prince's answer, which is 7.29625. Okay, so we substitute this into the formula. This will be S1 is 92 Okay, 92.25. 255 minus x2 is 92 point what 733 over our output, which is 7.29625 square root of what 1 over oh sorry, we didn't find the square root of it. Please find the square root. Did you, or you found it already? Prince, did you find the square root of your answer here?
No, sir.
This is square, so you have to find the square root of it.
All right, sir.
Okay, so the square root of it is 2.7011. So 7011 here over n1, which is 8. Okay, plus 1 over 8. So do the calculation for this two and give me the answer. Yeah, what are you getting? What are we getting?
Sir, we're on it, sir.
Okay.
Sir.